So let us begin. Today we'll finish the discussion of what is a black hole, and then we'll start the curved space-time. And in the curved space-time part, there are a lot of things that I'm going to do today which are not all included in the notes. So please pay attention and stop me if you have questions and so. So this is part 4 that we continue. So in order to define in a precise manner what a black hole is, we need to have the precise notion of asymptotic region, and so therefore we introduce this notion of asymptotic in Minkowski space-time. And the idea here was that these have null boundary. Part of this null boundary is chi plus, which is a part of the boundary such that no point of the physical space-time lies to its future. So we got the notion of chi plus. And then the idea is to look at the causal past of chi plus, the region of space-time from which one can send causal signals to chi plus, so signals escape. So that part of space-time is not a black hole. If intuitively the idea is that if in fact there is some other part of space-time, in other words, if the causal part of chi plus does not actually cover all of space-time, then the intuitive idea is that there should be a black hole. Look at J minus is supposed to be a causal past. Minus means past. This is past. J symbols J stands for causal. So look at the causal past of chi plus to define a black hole. And this is essentially the correct idea, except that there is one last caveat. The last caveat is the following. For example, you may imagine a space-time which actually is asymptotically flat. It looks like Minkowski space almost, but there is actually naked singularity, which is space-like. So one might have a naked singularity, which is space-like here. Then there will be a region which will not be accessible from future than infinity. We're going to try these colors now, blue and green, which might be more visible up there. So we might actually have a naked singularity up here, and then the statement is that if I now look at the past null cone of these 2 points, in other words, I obtain some region up here, and it is clear that if I have light ray coming from this, then that is going to get stuck in the naked singularity. It will not actually come out to infinity. So if I got a point up here, then this light ray can go out to infinity. If I have a point up here, the light ray would in general get stuck up here if it actually passes through this region. And if I have a point much further, then there will be no problem. So there will be some region from which the light rays will get stuck, will not be seen from infinity, and yet we don't want to think of this as a black hole because there's no horizon, it's a naked singularity. So, I mean, this is not the only reason, but this is a type of reason for which we need to add another condition. And the other condition we want to say is that if I look at the causal past of chi plus, then, so the idea up here is that if I look at the causal past of chi plus, then that should include a region which is globally hyperbolic. So now what does it mean by globally hyperbolic? It just means that so that I can specify initial data on a space-like surface which will determine the solution everywhere. In other words, there is actually a deterministic solution up here. Right? So the idea up here is that we look at we look at this J minus of sky plus, and we want to say that this is included in the region which is globally hyperbolic. We might need to define precisely what global hyperbolic means. I don't know if the notes do that or not. It takes a little time to give all the definition, but the crux of the idea is that a space-time is global, a region is globally hyperbolic. That is to say, initial value problem that the initial value problem is well defined in this region. In other words, there is a determinism. Initial value problem is well defined. That means if I give myself initial data on a space-like surface, you can give initial data on a space-like surface, which determines the solution everywhere in that particular region. So can give initial data. That determines the solution everywhere in the region. So this would not be the case because I cannot really, if I look at the past up here, then I would have a problem of getting a globally hyperbolic region up here. And so the statement is that so that we add this particular condition to our definition. Okay. Then what we need to do is to check. Let's see, what is the next? So we have this definition of asymptotic flatness now, and we have definition of what a black hole is. Yeah. So now the black hole is. So we'll define space-time. And asymptotically Minkowski space-time. Is said to admit a black hole. Okay. So a black hole region. If I look at the causal past of sky plus, if the causal is included, in the globally hyperbolic region, so it's included in a global hyperbolic region such that and this is the point, and the full space-time M is bigger than the past of the past of this sky plus. So M minus J minus sky plus is non-empty. And then the black hole region B is exactly this. It just means minus. It means all points which are M, but not included here. So this is the set minus. So set minus. This is the black hole region. So black hole region is just defined to be M minus J plus. So now, this is our definition of general definition of black hole. I have to say that this actually is used quite critically in proving various global theorems and important physical properties of black holes. It's not some, just, well, we just put it and then we forget it. I mean, it really lies in the global theorems. I mean, for example, the Hawking's theorems about the area increase and so on, they depend on that. And then by horizon, we just mean it is a boundary in M of the black hole region. That's what we mean by horizon. Sometimes it is called event horizon of a black hole. There's various kinds of horizons in general relativity. We'll see that. So this is called the event horizon of a black hole. So it's the boundary of that. So it is really, we can call it the horizon edge. It's a boundary of this region. So I get J minus of square plus black hole region. Well, black hole region is M minus that. But of course, if I just take the boundary of this region up here, so if you had a gravitational collapse, I don't know if I draw this picture before, but if we had a gravitational collapse and that forms a black hole, we're going to see it in a minute today. So this would be the singularity, R equal to 0. This is a non-rotating black hole that collapses, that's where it collapsed, and then we got. So the statement up here would be that this is sky plus. Past of sky plus is this region, and this region is the boundary. So this region up here is J plus, sorry, J minus of sky plus, this region, and we look at its boundary, and that is a horizon in this case. And you can consider more general black holes, and you can consider black holes which are going to study in a minute. Or you can consider, for example, black holes in presence of cosmological constant. The global structure is different, but nonetheless, the black hole is defined as the region, the region from the space-time, from which we cannot send causal signals out to infinity. So you always have this notion of infinity required. It's a bit surprising, if you like, because that means that in a cosmological constant, where we do not have asymptotic regions, we do not have asymptotic flatness, and or asymptotically intersitters. Let's talk about asymptotic flatness. In the case when the cosmological constant is 0, then the statement is that the cosmological models that we normally consider, they are not asymptotically flat at null infinity. And so strictly speaking, we do not have a notion of a black hole, which is what is used in various theorems. You do have an intuitive notion of a black hole. You can say that, well, there's some exterior region and the signals cannot reach there and so on. But I think that this is a interesting but more mathematical open problem in general relativity, which is really, really basic. There are a few such problems which are very basic. I think it would be nice if, in fact, we had a much more general definition, which includes this, but it's also applicable in a wider class.
Can you explain a little bit further why if you make a singularity kind of destroys the initial data, or?
Oh, yeah. So the statement up here is that if I give my, so this region is not globally hyperbolic. The reason is because, so if I look at this region up here, if I give myself say initial data here, that initial data, I will not be able to propagate it unambiguously to future space like slice like that. Why? Because this is singularity and this space line, and therefore, in fact, I can, things can come out of the singularity in an uncontrolled fashion, and therefore I would not have a unique deterministic evolution from one Cauchy from one space-like surface to a future space-like surface. If I did not have that region, then I would have Einstein's equations, Maxwell's equations, they're hyperbolic. So I actually give myself data here, then I'll get up data here. I should say this is all, I emphasize here, this is kind of intuitive heuristic. and heuristic argument that I'm giving up here. And the reason for that is because I don't want to spend too much time on the notion of what is exactly globally hyperbolic and so on and so forth, but just to make you at ease that yes, we did need some such, please.
So you say that, of course, that if we have cosmological constant that's not well defined because we don't have an asymptotically constant spacetime, so.
No, but we do have asymptotically de Sitter spacetimes.
Yeah. So
and
can you hint us what's going wrong in this construction?
Right. So this was the question again that came up here. So we got this notion of asymptotic Minkowski spacetime. So this is a detour to answer the question that was just asked. So we're talking about asymptotically Minkowski spacetime, and I wrote down the definitions. I started on this board, if you may recall, and I put a condition right here on the top. And that condition was that, in fact, if I look at GAB, Einstein tensor, which is RAB minus 1/2 R GAB, this is the same as that, is equal to 8 pi times GAB. We use this. And we use this and GAB. Omega minus 2 times TAB as a limit. The boundary scar. That's what we use. So here I did not have a cosmological constant up here. And this is what Tell told us immediately, that Scry is null. And in fact, you can introduce coordinate systems and so on. Given this structure, you can introduce coordinate systems in the neighborhood of Scry to see that explicitly, that shows explicitly that in fact the physical space-time metric is approaching a flat metric without a cosmological constant, so flat metric at infinity. If we have a cosmological constant, then we can, the modification of that definition is to say that a space-time is asymptotically de Sitter or anti. Let me just do de Sitter or anti de Sitter then, because I don't want to take too long to write. It's asymptotically de Sitter. So lambda is positive. If the conditions are the same, except that this is just replaced, right? It's not very profound. If this is replaced by, again, GAB right? And then the statement is that 8 pi times TAB, and then the statement is where omega to the minus 2 times TAB has a limit. I mean, we're just saying field equations hold asymptotically. But because of this constant, I mean, I had a conformal transformation between the richest scalars, and if you look at that, and we did that in the class, it was in the middle board up here. If you look at the conformal transformation of the richest scalar, so in this case, we find that in fact, the null normal, NA, which is just defined to be equal to grad omega. This is just a null normal to Scry. Omega is equal to 0 on Scry, therefore gradient of omega is a normal to Scry. And then what we saw was that this null normal, in this case, is time-like. In the case of de Sitter, in the case of anti-de Sitter, it would be space-like. So in the case of de Sitter, this is time-like. Therefore, Scry is not null, but Scry itself is space-like. So Scry plus looks like that, and our null normal NA is time-like. So it's just space-like. So that's the only difference in this case. So again, what we would say is that, so the definition would be the same, an asymptotically de Sitter space-time. So everything else is exactly the same as what we have done. Only this condition is replaced by that condition. And then we know, as a consequence of field equations, that Scry is actually going to be space-like. And then we're going to say that, well, if there is it would admit a black hole region, if the causal path of the Scry plus admits, is included in the globally hyperbolic region, and it is true that the causal path is not all of the manifold. So therefore, there is some region from which signals cannot escape to infinity. So everything I've written down up here without a word of change, without any change at all, is again a definition of black hole in that case. So if you just want to see it quickly for those who are a little bit familiar, so the statement up here is that here we saw a star which collapses and forms a black hole. So in the de Sitter case, if you've got a star which just collapses and forms in the asymptotically de Sitter space-time, if your corresponds to a constant, a star collapses and forms a black hole up here, then again, you again have this some region up here like this, and then you've got sky plus up here, and you've got sky minus up here, and then again this region from which there is more structure in the asymptotically de Sitter space-time. There are also other types of horizons called cosmological horizons, which are not relevant up here for what we're talking about. And again, so this will be the picture up here, and then the statement is that the signals from this region will not be able to go to scramble. So signals in this region will actually go into the singularity, and therefore this region up here is the black hole region. So again, the causal path of Scri is not of all of space-time. So it's very similar. It's in fact identical. The only difference is that the structure is exactly the same. The difference is that Scri is space-like rather than null, and that does have some consequences. But for black holes, it's not very. At this level, it's not very. Any other questions? Okay, good. So now, of course, we have got this definition. So we better check if, in fact, we have the Schwarzer space-time that we constructed is in fact the Schwarzer space-time that we began with, and the classical extension that we constructed, and all that. If in fact there is a black hole in that space-time, so we return finally to Schwarzer space-time very quickly. And for the Schwarzer space-time, remember that the metric was given by the full 4-dimensional metric was given by the in the region 1. The region 1, which is kind of the asymptotic region from which we begin, and then we use what is called the Schwarzer coordinates, and then I get here minus 1 minus 2a more r times dt squared plus dr squared upon 1 minus 2a more r plus r squared d omega squared. So that's what we got up here. Now remember what we did in Minkowski space-time to see if in fact the space-time is asymptotically flat, and to attach a boundary which we call Scri plus, and similarly Scri minus. So to Scri plus, what we did was we introduced a null coordinate along which we can go to Scri. So we introduce a coordinate u. In Minkowski space, we introduce u, which is t minus r. Not very surprisingly here, t minus r is not going to be null, but t minus r star is null, and r star is a coordinate that we had defined before. And then I leave this as an exercise. You just define this, and then we find that dA squared has a very simple form. In fact, all this 1 minus 2a more r, etc., that all simplifies greatly, and we just get here minus 1 minus 2a more r du squared. So this is an exercise. Please do it. It's very simple. It will take you 5 minutes to do it. This is elementary calculus. To check that this actually is what we get, du squared minus twice du dr. And the pleasant surprise is that, in fact, you don't get r star anywhere. You just get r. R here, plus r squared d omega squared. So if you like, I mean, that's a bit surprising in the beginning. How can r star just disappear? But it does, and so that is a little exercise that you should do. So remember that if m is equal to 0, we get Minkowski space. And in fact, in Minkowski space, we had minus du squared plus minus 2 du dr plus r squared d omega squared. So it's very similar to that. All that changes is just this factor up here. And therefore, in fact, again, and this factor, as r goes to infinity, this factor, in fact, does go to infinity. So the metric does turn to Minkowski space. And so not very surprisingly, you can again define omega. I just define omega to be same as Minkowski space, 1 upon r. so outside some region. In Minkowski space also, we just excluded r equal to 0. We took some r0 and defined the conformal factor outside. So because we just need the conformal metric near scri, we don't need to know what it is doing in deep inside space-time. So again, if we use this thing, then we define here ds hat squared to be equal to omega squared ds squared. And you substitute for r to be omega, dr to substitute in terms of omega, and since I multiplied by omega squared up here, you find that this is in fact equal to minus 1 minus 2m omega times omega squared du. So omega squared du is what we had in Minkowski spacetime. Now we get 1 minus 2m omega. So one factor which goes to 0 even faster. Minus plus 2 du d omega plus d omega, little angular part up here. So at scri, this term is just 0, and at scri the metric is just given by exactly the Minkowski metric up here. So this is the metric at scri, so if you like, ds hat squared. At scri, again this hatted equality only means at points of scri, we got this equality. This just becomes 2 du omega plus little omega squared. And then the coordinates are u omega, and omega equal to 0 at scri, and then theta and phi. And therefore we get perfectly fine the conformal completion up here. Please pay attention because this is going to be the key to the curve space time. So please do pay attention up here. And now, so we get scri plus up here. So basically, we started out with this region, r equal to 2n. And now what we've done is really added this boundary up here. So this scri plus is this boundary that were added, and this boundary is where omega is equal to 0, and what is going from minus infinity to infinity is this u coordinate up here, and theta and phi, which are in this angular part, are just going around. So each point up here is a two sphere of unit radius, because the metric is just d omega squared, the unit two sphere metric, and so we get this scri plus up here. So now I can do exactly the same thing, namely to get scri minus, namely instead of defining u, I define the advanced coordinate t plus r star, and then I again get the metric which I can write down, and again so the metric up here will be ds squared will be equal to minus 1 minus 2m over r times dv squared, but now I get plus du dv dr plus r squared d omega squared, and that is just because u is equal to t minus r star. I'm substituting for dt, so dt is going to be equal to u plus r star, and here t is going to be, or dt is going to be equal to dv plus dr star, minus dr star. Here it was plus dr star, now it's going to be minus dr star. That's why this sign changes up here, not very profound. And again, you choose omega to be equal to 1 upon r, outside some r equal to r naught, and we get conformally completion of space-time, ds hat squared, and that is just given by, ds hat squared, this is given by minus 1 minus 2m. Now in this case, omega times dv squared instead of u squared. And here I get the sign changes. The sign changes basically because we're going from dr to d omega. Since omega is equal to 1 upon r, when I take d omega, I get an extra minus sign. That's why this minus sign becomes plus, and this plus sign becomes minus. I'll just get here dv d omega plus d omega. This r squared, both cases, is absorbed by the conformal factor omega squared. So you just get that metric. Again, if I forget the mass, I get exactly Minkowski metric. So we see that in fact it is approaching the Minkowski metric up here, and therefore for scri minus, I'll get this thing. So basically, what are the various patches that I cover? With the ut coordinates up here, so if I look at my original picture of crustal spacetime, the crustal spacetime of the maximal extension, so I got this spacetime like that, this is r equal to 0, r equal to 0, And the physical space-time is everything bigger than r, with r bigger than r0, so r positive. So this is all physical space-time up here. We start here with region 1, and then the statement is that this coordinate that we started with u, this coordinate u includes chi plus, u equal to infinity here, u equal to minus infinity here. So this u coordinate, so this was region 2, 3, and 4. So this u coordinate covers region 1 and 4. And the v coordinate then covers region, this region up here, this region up here, because it includes this and it goes up. Yeah? And here then v is equal to minus infinity, and here you got v equal to infinity. So we got overlap, and of course on overlap they're all smooth. So if you wanted to get the singularity, it's better to use a v coordinate. If you wanted to get chi plus, so v coordinate also gives us chi minus. If you wanted to get the black hole singularity, it's better to use a v coordinate. If you wanted to get chi plus, it is better to use u coordinate going in this region up here. So chi plus is in here, and then it will include a singularity, which is the white hole singularity. So these are the two coordinate patches. These coordinate patches are known as Eddington-Finkelstein coordinates. This is the retarded Eddington-Finkelstein coordinate u, omega or u r theta phi is retarded Eddington coordinates, and v r theta phi are advanced Eddington-Finkelstein coordinates. So these are u r theta phi and v r. These are that. And they don't cover all of classical space-time, they don't cover this other patch, but that is not that of interest to us because this is the other asymptotic region. We're mainly interested in this patch up here, which is regions 1 and 2, the black hole singularity and the asymptotic region 1. And because of that, it's better to use, and that is actually covered by this advanced Eddington coordinates in green, and that is what, just keep in mind. Okay. Any questions? Yeah.
But why can't I take u and v coordinates at the same time?
Yeah, you can, but the statement, you could take u and v coordinates at the same time, eliminate. But that's what we did last time. When we did the classical extension, that's what we did. But then the statement is that it's not that 1 upon r is a conformal factor, because remember r is a complicated function of u and v now because of r star. I mean, r star is a nice function of u and v, but r is not. So I mean, there's not. It's just here it is so trivial. The other case you have to do a little bit more work. You can use those coordinates if you wanted, and that's what we did in the
It's
crystal.
really useful to understand how the conformal factor behaves easily.
Yeah, but it is again asymptotically. It is just going to go like 1 upon r. R star and r. Maybe I should write down explicitly. R star I always get signed wrong, so let me just make sure that I get the sign. R star is equal to r plus, I think. Plus 2m. Yes, plus 2. So if I take r outside the bracket, I'll get 1 plus 2m over r times this. Therefore, at infinity, this term is blowing up logarithmically, but it is 1 upon r. Therefore, this term is completely subdominant compared to the term r up here. So r star and r at infinity behave the same. Near the horizon, they behave very differently because r is just 2n there, and r star becomes minus infinity there. That's why it's called the tortoise coordinate. It approaches the horizon very slowly. Yeah. So we can use little u, little v. You can use capital U, capital V, and of course you can write down the classical, the conformal completion, getting both chi plus and chi minus using capital U and capital V. There's no problem. It's just that things are not as transparent as they are here. Now last time Lucas asked this question about, well, I did this conformal completion, right, which gave me chi plus and chi minus. is there some way, is there some reason why I could not have another boundary which would actually include also the singularity? Because we saw, singularity is not part of Scri, but in fact there is another boundary up here, then that would also be, supposing I could do a conformal completion, then this new boundary up here would be also part of the null boundary, part of Scri if you like, and then if I look at the past of that, it will include the black hole region. Then won't I get some contradiction? You did not ask in this language, but you are saying that, well, do I know that I cannot do some conformal completion in this region, that I don't have a piece of boundary in this region? And the answer is yes. Namely, that yes, we do know that we cannot do the conformal completion. It's just that at that time, when Lucas asked this question, I had not done this conformal completion, and therefore the situation was, could not explain very quickly. But now we can, what we have in mind up here. In other words, indeed, there is no piece of boundary which is close to the singularity in this conformal completion. So this is just a remark. Remark is that no singularity cannot be part of conformal boundary. In our definition. Of asymptotically Desider space-time, asymptotically mini-Haskell space-time. Now, how do I see this? Well, remember we can look at the curvature tensor. This is the Riemann tensor up here. And I can contract two of these indices, and that gives me the Ricci tensor. Okay, so this is the same as, in fact, the Riemann tensor, when it's first defined, has this index structure, and then what we're saying is that, in fact, I'm contracting these two things. So that will be that's of course the Ricci tensor that we're talking. So in 4 dimensions, Riemann tensor has 20 components, and the Ricci tensor has 10 components. So half the information is in the Ricci tensor, roughly speaking. This is all heuristic. And then I got the Einstein tensor, and Einstein tensor is just RAB minus 1/2 RGAB. So scalar curvature, of course, is constructed by contracting these indices. So it's also part of the Ricci tensor. So Einstein tensor is part of Ricci tensor. It's the Ricci part of the curvature, I should say. It is a Ricci part of R. And then Einstein's equations say that this is what is equal to 8 pi times TAB. So it's quite useful, it's not a precise statement, but it's quite useful to say that the Ricci part is determined by the matter, and the rest of the 10 components are somehow intrinsically gravitational. So what are the rest of the 10 components? Well, the algebraic symmetries of the Riemann tensor tell us that we can always decompose it. The rest I was just talking about, C, B, C, D. This is called the Weyl tensor. This is the rest. It also has 10 components. Ricci tensor has 10 components. This has 10 components. So together, they are the independent parts of the Riemann tensor. And then the Ricci part. And the Ricci part is just given by GAC as DB minus GB. Where this tensor S is RAB minus 1/6 RGB. So we're removing different parts of trace basically in defining the Einstein tensor and defining this S tensor up here. So this is the decomposition. So the statement that Riemann tensor can be divided in this particular part, and so this part is the Ricci part, because Ricci minus a part of this trace, so it's the Ricci part, and that is determined by matter. And we think of this as being kind of the gravitation part of the Riemann tensor up here. So this is the gravitation part and this is the Ricci part. For example, if you got Friedman models, of course there's a lot of symmetries, but in the cosmological models, we only have the Ricci part. The wild part up here is 0. The Riemann tensor only has the Ricci part. It's completely determined by matter, if you like. There's nothing else. On the other hand, we're doing Schwarzschild, and Schwarzschild solution, in fact, Ricci part is 0. There is no matter, right? So in Schwarzschild, we got Ricci part equal to 0. Therefore, RABCD is just the wild tensor. This is the wild tensor. It's going to be useful. Please, this is, I'm doing another side thing up here, but this is going to be useful very much all along. So, what are the properties of this wild tensor? Well, from the definition itself, it turns out, you just check it if you like, it follows that the wild tensor has, first of all, the same symmetries as the Riemann tensor. So, it is antisymmetric in these two indices. It is antisymmetric in these two indices. And if I flip CD with AB, it doesn't change. These are the properties common to the Riemann tensor. CD, AB. So of course it's antisymmetric in CD and AB. I don't write it again. So if I just flip CD with AB, it doesn't change. So these are the properties which the Riemann wild tensor inherits from the Riemann tensor itself. And in addition to that, it has a property that it is trace-free. The trace of the Riemann tensor is all in the Ricci part, so you would imagine that this would be trace-free, and that is indeed the case. So if I take CABCD, and if I take the trace, if I contract on A and B, of course I get 0 because this is antisymmetric. So I should contract on A and C, or B and D. So this is 0, and of course that's the same as contract on B and D. If I contract on any of these two indices, if I take the trace of this tensor, it is equal to 0. This is trace-free. So, as I was saying before, for Friedman models, cosmological models, they are conformally flat, which just means, that the CABCD is identically 0. So let me just write down that. Completely generally independent of Einstein's equation, just from differential geometry. It follows that if the metric GAB is conformally related to flat metric, then CABCD equal to 0. So in fact, if I do this, if I make in general, if I have a metric G hat AB, which is say omega squared times GAB, where GAB doesn't have to be flat, it doesn't have a solution. This is just G hat AB is equal to omega squared GAB. That's the kind of thing we did when we did conformal completion to describe. Then the wild tensor with this index structure is conformally invariant. So the wild tensor of this metric is the same as the wild tensor of this metric. If I lower this index, then I get some omega squared factors, but otherwise this. And therefore, if in fact, in this case, let me call it G hat. So if in fact, if eta was, if I put for G eta, since the eta is flat, so in particular the wild tensor is 0, and therefore the wild tensor of this is actually 0. So in Schwarzschild metric, the entire curvature is in the wild tensor, is all in this gravitational part. I'm spending some time on this because, for example, in the literature you'll find something like Penrose's wild curvature hypothesis. And the point that Penrose was trying to say in this wild curvature hypothesis is to distinguish the Big Bang singularity from the black hole singularity up here. In the black hole singularity at r equal to 0, in Schwarzschild, of course, the Ricci tensor is 0 because the Ricci tensor is 0 entire space-time. Therefore, what blows up is a Y tensor. In the Friedman model, so this is just a aside, those you already know about Friedman model. In the Friedman model, the cosmological case, the Ricci tensor of course is not 0, but the Y tensor is 0. And the Ricci tensor blows up at the Big Bang at t equal to 0. So the idea was that this was the initial singularity, and this is the final singularity. Final means at the end of time, so to say, because it is formed by the gravitational collapse up here at late times, whereas the Big Bang was really at time t equal to 0. And so this is a fact about Schwarzer, this is a fact about Friedman, and what Penrose did was to generalize this into a general conjecture which says that the initial singularity should always be such that the Y tensor is actually 0 there, and what diverges is the Ricci tensor, whereas the final singularity has the opposite part of it. Now, this is a proposal. It's a very interesting proposal, but there are problems associated with it. So I don't want to discuss it in great detail, but I just mention it because you hear these terms, wild curvature hypothesis, etc. That is what is coming. Let's come back to Schwarzer, where the Y tensor actually blows up. Now, the Y tensor blows up. That means that the Y tensor of G hat AB also blows up. Right? This Y tensor, because that is conformally invariant, that actually blows up here. Right? And therefore, the metric G hat AB, so in any conformal completion, the metric G hat AB cannot be regular. Cannot be regular at the singularity r equal to 0. So, when we define asymptotic flatness, what we did was, we said that we are given a physical space-time and we conformally complete it by conformally rescaling it by a conformal factor omega. This was physical and this was the conformally rescaled metric. And such that this is smooth at the boundary, and then omega has property, omega equal to 0, grad omega is not equal to 0, etc. But what we see up here is that necessarily, if I make a conformal computation, I will find that the curvature actually blows up at the singularity, the wild curvature. Wild curvature is conformally invariant, which means that the metric G hat AB, whose wild curvature is C hat AB, blows up. So C ABCD blows up, that means C hat ABCD blows up, and therefore the statement is that this conformal, the metric G hat AB cannot be regular there. And therefore it could never be part of a boundary in a conformal completion. So the part of the boundary you get, this clever conformal completion, is such that a priori you would think, well, wait a minute, I mean, I got this, after all, I'm rescaling the metric, and I got a singularity, but maybe rescaling the metric kills that singularity. The answer is no, because the wild tensor actually blows up there. Okay, this is a subtle point. If you have any questions, please ask me. If you don't follow all the details, it is not going to be essential for what we're going to do in the future, but if you do follow it, it's going to be very useful. Namely, in our definition of a black hole, we needed the notion of asymptotically Minkowski spacetimes. And then we needed the boundary scry. And the point is that the boundary scry that we will get is really comparable to the boundary scry of Minkowski spacetime. It wouldn't have additional pieces, for example, near the singularity. A priori, it was not obvious, but it's true. That's what it is. Any other questions? Yeah.
Okay, so this does distinguish singularities of cosmological type from those from the black hole, because for cosmology you can just always make these Penrose diagrams properly because you can just rescale everything. Does that mean that, like, what does that imply for like the propagation of signals through something like a Big Bang singularity? Because, like, you know, usual Maxwell fields are conformally invariant, all that kind of stuff.
Yeah, so this is the point of view that some people take, and particularly Penrose, that in fact, somehow things conformally invariant, and that is certainly true, that conformally invariant fields would actually probably be able to propagate through the Big Bang singularity. And then he has the hypothesis, which would say that all fields become massless and conformally invariant, and that I think is very difficult to understand. So electron has to lose mass, and its mass is time dependent, and so there are issues there which most of us don't understand in his ideas, and there are also, at least when I've seen it, I'll always ask him about these questions, and these questions have not been resolved. There are also tensions. If you really follow the idea very clearly, the full ideas that he has in the last year or so. I just saw him a few months ago in Warsaw. We had a very, very long discussion, and the statement is that there really are open issues there about to make that paradigm work. But mathematically, it's certainly true that conformally invariant field equations, if you have conformally invariant field equations, those fields can propagate across the Big Bang singularity, but they would not be able to propagate across the big
So
bunch.
is there a sense in which you can extend these diagrams beyond those singularities? Or?
I mean, if you just yeah, I mean, you said that there is a singularity, but that's actually there's actually a Ricci singularity, but my world is conformably flat, and therefore I go back. So you could do that, right? Yeah.
Yeah, I have a question. I think, maybe I'm wrong, but I think there is probably some tension with the BK conjecture, in the sense that if you have anisotropies in the cosmological model, then the Weyl tensor is not sigma, right?
I mean, that's my problem also. One of the problems I have with the Weyl curvature hypothesis. As soon as you have got BKL behavior, then so Penrose's response to that is that yes, of course, the initial singularity is very special. So you would not have the BKL type behavior. You really have the Friedman type behavior in the distant past. That is the physical principle you would like to impose. But it's certainly true that if you have got BKL behavior, I mean, if you have anisotropies, then the Weyl tensor actually does blow up. If there is time, I doubt that there will be time. But if there is time, I'll discuss this further in the discussion of gravitational waves, because that is really the issue of the gravitational waves up here. Okay, so this is the end of the fourth part, which is what is a black hole. And now what we want to do is to start the discussion about Kerr space-time. Okay. Now the story about the Kerr space-time, as we'll see today and also Wednesday, is quite dramatic. It's quite dramatic on both kind of scientific part as well as from human part. Namely, this, Schwarzschild discovered this solution, right, during the first World, and a year or two after Einstein's discovery of general relativity, the field equations, and then people looked for rotating analog of the Schwarzschild solution, because they thought of the Schwarzschild solution as a gravitational field of a point mass, and they wanted to look at a spinning particle. What would the solution be? And people really tried quite a bit. And I should say that in those early days of general relativity, almost all the work was in trying to find exact solutions. So it's not that there was a huge community, but majority of the work was focused on that, and they did not succeed. And finally, Roy Kerr, who was a New Zealand mathematician at that time at the University of Texas at Austin, discovered the generalization, which we will now discuss. So it's pretty dramatic that this actually happened. And then, very quickly, Roger Penrose and other people understood the global properties. And the global properties are best, most thoroughly analyzed by Brandon Carter, global properties of Kerr solution. And they were presented for the first time in this very famous Lejeus summer school in the Alps in France. And that chapter has been reproduced, and I put it on our web, his chapter which actually does this. Now, if people would like to understand, would like to understand the global properties more, we're not going to, we're just have a little more than a lecture for curve solution. This is an excellent, excellent reference. It really is extremely thorough. The very first article did everything. It's not incremental, so to say. Also, those of you who are taking the course for credit, so this is the first topic for your term paper. I'm going to give more and more topics that if you could write down a term paper or 5 to 10 pages based on the global properties of curve solution, incorporating what we're doing in class, but extending it more using this Bernard Carter's article, which is on the web page. Okay. So then, suddenly the properties of black holes, sort of people started analyzing. Hawking and Carter used Penrose's notion of null infinity to really analyze its properties in much more great detail, proved some very seminal theorems, and so on and so forth. Now, as you probably saw, and we're going to see it, the curve solution was actually was not discovered first in the like Schwarzer coordinates. The Schwarzer coordinates are called Boyer-Lindquist coordinate, but in fact was discovered using coordinates like this. Why? We're going to see just now. And that discovery has kind of a couple of very dramatic events, which I will describe as we come to them. So, what was the idea? Why is it that Kerr succeeded in actually finding the generalization? Various people have actually tried, but had not succeeded. Well, because he looked at this Schwarzer metric to begin with in a specific way. And these ideas are called Kerr-Shield solutions. So the Kerr solution is a special case of a family of solutions which are called Kerr-Shield. So now we're doing the part 5, Kerr spacetime, Kerr black hole. And here, first we're going to do global structure, understand it. We will see that the nature of the singularity for the Kerr spacetime is quite different from that in the Schwarzer spacetime, and we would like to understand that. And then, the second part, we'll do geometry and physics. This geometry of Kerr spacetime then has very interesting physical implications, physical consequences, and that's what we'll study. We did that for Schwarzer. Kerr, it is even much more interesting than Schwarzer. So these solutions are called Kerr-Shield solutions. And so let's begin with that, Kerr-Shield metrics, or Kerr-Shield metrics. So the idea up here is to start with this notion up here, right? Namely, the Schwarzer metric in these coordinates, which are advanced, actually includes this patch of space-time. Not only does it contain the asymptotic region, which is covered in the Schwarzer coordinates, but it actually contains also the singularity. And in these coordinates, you see that nothing goes wrong at r equal to 2n. This term goes away, but there's nothing there. Nothing at all goes wrong. It's just that this term goes away. This is perfectly well-defined hyperbolic metric. So there is no accident at r equal to 2n in this metric. So we see that r equal to 2n is a spurious singularity for the Schwarzer coordinates that we've seen already. But we see that in this case also. R equal to 2n is a good. There's nothing wrong. Therefore, we can start with this particular form of the metric. So we begin with Schwarzer and we write it. First, we begin with observation. And the observation is the Schwarzer metric can be written like that in that particular form. I'm just going to write exactly the same form, but just move this m term at the end. So it is just going to look like minus dv squared plus 2 dv dr plus r squared d omega squared. And then I move it on the other side, so I get plus 2m over r times dv squared. Now this is just a flat metric. In fact, when we did Minkowski completion to include square minus, we got exactly this metric up here. This is just a flat metric up here. So remember that V was defined, I just want to write it once again. to be equal to t plus r star. These are Schwarzer coordinates. However, if I look at this as a flat metric, I have to define a coordinate t, capital T. So I would like to write down V as capital T plus R. Because in Minkowski spacetime, V was just T plus R. So this capital T is going to refer to Minkowski spacetime, so there's going to be different. And this R is the same R as here, but I don't have R star, but I have got R. So if I define this, then this metric up here just becomes minus dt squared plus like dr squared plus r squared d omega squared, or same as minus dt squared plus x squared plus dy squared plus dz squared. Really Minkowski metric, but of course we got plus 2a bar r times dv squared plus 2a bar r times dv squared. So in this form you see explicitly, I mean it's not that it's too difficult to see from the other Schwarzer form of the metric, but in this form is really Minkowski metric plus a term like that. Furthermore, this dv. Remember, v is a null coordinate. V equal to constant on null lines. Therefore, dv is actually null vector. So if I take dAv or grad AV, this is a null vector. And therefore, of course, I could just absorb 2a more r here, and if there is null vector and I multiply it by something, it's again null. Right? So this is a null vector. So remarkably, Schwarzer metric is just Minkowski metric plus outer product of two null vectors. In other words, if I write down the Schwarzer metric GAB is equal to eta AB plus KAB, where Ka is just equal to 2a more r times eta AB. This is null. This is null vector with respect to eta AB. So this is null vector. You can just check that, and I'm going to leave some exercises. Please do them because you sort of understand all kinds of subtleties. And they are simple subtleties, but it's important to get that right. So you find that that Schwarzer metric has this very simple form. Is equal to flat metric plus outer product of two null vectors. So this is the observation with which this is the observation that was so Kershel together. There is a whole bunch of papers in which they were looking at solutions of Einstein's equation of this form, where k is not this null vector but some null vector, and try to understand what happens in that case. And we're going to see perhaps next time exactly what happens. So they were looking at that. I'm telling you a story logically rather than historically. So logically, there's something funny that is really amazing that is true about this. And that was discovered by a graduate student. So this is inspiration for all of you, right? So a graduate student, Vasilis Alexandropoulos, in 1978, discovered the following incredible fact. I was a postdoc, he was a graduate student, we were close friends. For some reason, he was not even going to publish it, and I kept asking him to publish it, so finally he did publish it. It's in JMAP space. He found the following remarkable fact. He said that, well, supposing, and it's more general than this, so let me write down the Alexandropoulos theorem. Supposing I got a metric G tilde GAB, and I got a metric G tilde AB. GAB and G naught AB. I got two metrics. In this case, G naught AB is flat, but he said it can be any metric. Supposing GAB has a form G naught AB plus KAKB. G naught AB is a solution to vacuum equations. In our case, in this case, for the Schwarzer case, G naught AB is just eta AB. So of course, the flat metric is solution to vacuum equation. Then he's asking, where is G solution to the vacuum equation? And the statement is that he found this, to me at least, remarkable theorem, namely, the Exodopolis theorem. He showed that if think of this as G naught AB plus HAB. I mean, I'm just calling this HAB. There's no new content to this. Just call this HAB. So I got a vacuum solution. I got this HAB, and what he showed was that if this HAB is a solution to linearized Einstein's equation of this background, then G naught plus H or G naught plus KK is an exact solution. You see, Einstein's equation is highly nonlinear. I can't take a nonlinear solution and add to it a linear solution and get an exact solution. Something miraculous happens here. And it's not just when there's a flat metric. Vasilis' theorem is completely general. It says that if in fact G naught AB is a vacuum solution, and then G naught G, and just define GAB plus KA, find some K such that KA KB, HAB is equal to KA KB if you like, is a linearized solution. So just one second, yeah.
So before K was null with respect to G, now K is general, or
Now K is null inside. K is, thank you. So we are already given G naught to begin with, so we just take this to be null with respect to G naught. Okay. So if HAB, KAB, zero, this is to linearized. On the manifold M with the metric G naught AB, then G is an exact solution. So I can take a, I mean, it's not easy to, another way to put it is that it's not easy to find linear solutions of this form. If you could find a linear solution of this form, I can just add it and I get an exact solution. So that is a very remarkable fact. And this is in Journal of Mathematical Physics. Volume 19, page 1607, 1978. Now, what I'm surprised. I reread this paper just this morning again, just to see again what did you do. And what I'm surprised about is that he only states it one way. He says if this is a linearized solution, then we got an exact solution. But I believe that the converse is also probably true. Namely, if in fact you have got GAB and G naught AB both, we got GAB and G naught AB both as exact solutions of this particular form, then this is also a linearized solution on G naught AB. That must be true. So it's really good. So one of the term papers could be, this will be more research oriented, which is a small calculation, not a very deep calculation. You'll see the paper is the main result is just 1.5 pages, right? I mean, there's the introduction, it starts here, and the main result finishes here. So it's not even 1.5 pages, it's only 1 page. I'll put all this in the web page, but this will be good for you. So that will be great term paper because it will be at least original research in the sense that you're showing something which is not obviously in the literature. Namely, if in fact I got G as exact solution, G naught exact solution, they differ by K, KB of this type, then in fact it is this is a linearized solution, K, KB. Now, just quick remark and then I'll stop. The first remark is that already I was asked, Pietro asked me about when this K is actually null with respect to G naught. But you see, the interesting thing about this this form of the metric is that if K is null with respect to G naught, then it's also null with respect to G and vice versa. So the statement is that, so this is a little exercise that you should also do, namely show that K is null with respect to G naught, if and only if it is null with respect to G. So this is, so this will be an exercise, just quickly, just check that out, this algebraic exercise, look at the inverse and see what's happening. It also gets used to doing some simple calculations, but with just these tensors without using coordinates. You can use coordinates if you like, but it's not necessary. And these are algebraic, it's not at any given point you're talking about, there's no differential geometry involved up here, it's just tangent space at each point, that's what is it means.